Hi everyone. Last time we were discussing the periodic table and the periodic law. We said that in the periodic table, if elements are in the same group or column, then they have similar chemical properties. And those chemical properties really do depend on electrons. So we're going to talk a little bit more about electronic structure today. Now, Niels Bohr was a scientist in the late 1800s, early 1900s, who proposed that the electron in a hydrogen atom moved in any one of a series of circular orbits around the nucleus. So on the right-hand side, you can see the Bohr model of an atom. And in particular, this is for a hydrogen atom. Remember that hydrogen's atomic number is 1, so that means it has 1 proton and it has 1 electron. So in the center of this model, we have the nucleus, and then we also have an electron. And this electron can change orbits if it absorbs energy or releases energy. So for instance, in order for that electron to move to an orbit that's further away from the nucleus, it would need to absorb energy. Now it can also jump back down to an orbit that's closer to the nucleus by releasing energy. So what this tells us is if an electron is really far away from the nucleus, then it's going to have more energy. If an electron has more energy, that means it is more unstable. So remember that in the nucleus we have a proton, which is positively charged, and then electrons are negatively charged. So an electron wants to be close to the nucleus so that those charges can balance each other. And the closer to the nucleus an electron is, the more stable it is. But once it's really far away from the nucleus, it no longer feels that same attraction to the proton, and it becomes less stable. Now, this is a simplified version of the atom, and this model was replaced by a revised model in 1926. The revised model is called the quantum mechanical model, and according to this model, the precise paths of electrons moving around the nucleus cannot be determined accurately. So instead, we're going to use probabilities. Now, I like to think of this as runners in a race. If you take a picture of someone running, from that picture, you can determine the approximate location of the runner, but you can't determine its speed or their energy. And that's similar to an electron. You can either try to pinpoint the location of an electron, or you can try to measure their speed. But you can't measure both at the same time with a lot of certainty. You can really only know one or the other. Now, instead of circular orbits like in the Bohr model, the location and energy of electrons moving around the nucleus is specified using 3 terms: shell, subshell, and atomic orbital. So down below I have an analogy using these 3 terms. So let's say that we have electrons and they're attending a conference at a convention center, and we'll call that our nucleus. And let's say those electrons are staying at 4 different hotels. So Hotel 1 is really close to the nucleus, Hotel 2 is a little further away, and then if we go all the way over to Hotel 4, that is the furthest away from the nucleus. So each of these hotels we can think of as shells. So Hotel 1 is our first shell where an electron could exist, and we would label that n equals 1. So that shell is really close. And then Hotel 2 we'll call our second shell, or n equals 2, and then we keep going from there. Now, in Hotel 1, there's only one floor and one room. So, kind of a strange hotel, but that follows with where electrons can exist. And in Hotel 2, there are 2 floors. The first floor has 1 room, and then the second floor has 3 rooms. And then in Hotel 3, there's 3 floors, and again, the first floor has 1 room, the second floor has 3 rooms, and then the third floor has 5 rooms. And then in Hotel 4, again, we have floor 1 with 1 room, floor 2 with 3 rooms, floor 3 with 5 rooms, and then the last floor has 7 rooms. So we're going to call these floors subshells. And then we're going to call each of those individual rooms orbitals. So let's say we have an electron and it's in Hotel 4. And then we can further pinpoint where the electron is by saying that they're staying on floor 2, and let's say they're in the center room. So now we know the shell is 4. The floor is labeled P, and we'll talk about those labels in a bit. And then the room is the center room, which doesn't really have a label in our situation. We'll talk about that later. Okay, so let's dive a little bit deeper. We're going to start with shells. So let's kind of summarize what we talked about. So the location of electrons in a shell is indicated by assigning a number n to the shell and all electrons located in the shell. So down below we have, again, the Bohr model. And even though the Bohr model isn't as accurate as other models, like the quantum mechanical model, it's still a really useful two-dimensional way to think about an atom. So again, we have our nucleus in the center, and then we have our electron hanging out. And we have 3 different circles, and each one represents an electron energy level, or shell. So we can label each of these shells. We'll label the first one n equals 1. We'll label the second one n equals 2. And we'll label the third one n equals 3. And if we had more circles, we could keep going. Now, earlier we said that the further away an electron is from the nucleus, the more energy it has. So another way of saying that is the higher the n value, the higher is the energy of the shell and the contained electrons. Also, the higher the n value, the farther the electrons are from the nucleus. Okay, now within each of those shells we have subshells. So each shell is made up of 1 or more subshells that are designated by a letter from the group S, P, D, or F. Now, these letters are not arbitrary. They do come from a very early experiment that was trying to describe these subshells. So S, for instance, stands for sharp, P stands for principal, D stands for diffuse, and so on and so forth. So they're not arbitrary letters. They do come from a particular experiment. But the main thing to know is that the S sublevel, or subshell, is lower in energy than the P subshell, which is lower in energy than the D subshell, and that's lower in energy than the F subshell. So we'll put less energy next to S, and then we'll put more energy next to F. So not only do we have these different shells with different energies, but now within each of those shells we have subshells with different energies. So we're really starting to narrow down where an electron can exist in an atom. So the number of the shell to which a subshell belongs is combined with the letter of the subshell to clearly identify where an electron exists. So as an example, let's say that an electron is in a P subshell, and it's located in the fourth shell, n equals 4. We would call that a 4p subshell. So we're just combining the shell number with the subshell letter. So down below we have a chart, and this chart is summarizing the shells or energy levels, as well as the subshells or sublevels. And we can see that here we have 4 shells, n equals 1 through n equals 4. And the number of subshells that exists within each shell is going to equal the shell number. So for example, in the energy level 1, or shell 1, there's only 1 subshell. In energy level 2, or shell 2, there are 2 subshells. And that trend continues. So these are similar to the different hotels and their number of floors. So Hotel 4 had 4 floors, Hotel 3 had 3 floors, etc. All right, now when we're discussing electrons in each subshell, again, the number of subshells located in a shell is the same as the number of the shell. So we just went over that. Now we're also going to divide up these subshells into S, P, D, or F. So you'll notice again that in energy level 1, we have 1 subshell, and we're going to start with that lowest energy subshell, which was S. So remember that S is lower in energy than P, D, and then F. Now in energy level 2, we have 2 subshells, so we're going to add on the P subshell there. So we have an S subshell and a P subshell. And then in energy level 3, we have 3 subshells, S, P, and D. And then in energy level 4, we have 4 subshells, S, P, D, and F. So we can label these, for instance, starting at the bottom, 1S, and then we're going to jump to energy level 2, and we're going to label the S subshell 2S, and then we're going to label all 3 of those boxes in P as 2P subshell. And then we keep going. So we have 3S, we have 3P and 3D, and then 4S, 4P, 4D, and then 4F. So if, for instance, we have electrons in a 3D subshell, We're going to call those 3d electrons. Now we can take this a step further, and now we can also talk about atomic orbitals. So in our analogy from earlier, atomic orbitals were the different hotel rooms. So this is the last way that we can designate where an electron is located around a nucleus. So each subshell consists of one or more atomic orbitals. And these are specific volumes of space around the nucleus in which electrons of the same energy move. So you might already be able to tell that in an s sublevel, we have just one atomic orbital. And then in a p subshell, we have 3 atomic orbitals. In a d subshell, we have 5 atomic orbitals. And in an f subshell, we have 7 atomic orbitals. Now, all of these atomic orbitals have the same energy if they're in the same subshell. So all atomic orbitals in the f subshell, for instance, have the same energy. And then if we look at a d subshell, all of those atomic orbitals will have the same energy. And then in the p subshell, those 3 atomic orbitals will have the same energy. And again, the s subshell is lower in energy than the p subshell and its atomic orbitals. And then that's lower in energy than the d subshell and its atomic orbitals, and so on and so forth. Now, each atomic orbital has its own shape or volume. So, for example, you can see on the right-hand side that we have what's called a probability map of an electron's location. So down below it says the electron cloud of an s orbital represents the highest probability of finding an s electron. So basically scientists modeled where an electron might exist if it's in an s orbital. And they found that it's pretty spherical in shape. So if we draw a little line around here. So that told scientists that if an electron is in an s orbital, it's going to be within a sphere. So if an electron is in this 1s orbital, for instance, there's a spherical volume that it might exist in. Now, if an electron is in the 2s subshell, then it has a little bit more space that it could exist in. So it could be a little further away from the nucleus. So if we draw a little nucleus in there. And then the 3s orbital is even larger. So an electron in a 3s orbital, it could be pretty close to the nucleus or it could be really far away. We're not really sure. But we do know that the electron is somewhere within that volume. Now p subshells look a little different. They look like a figure 8 or a dumbbell. And a p orbital has 2 regions of high probability. Now remember that there are 3 p atomic orbitals. So the reason we have 3 atomic orbitals in a p subshell is each of those atomic orbitals are facing in different directions. So it has to do with the orientation. X, Y, or Z. So you'll notice this first p orbital lies along the x-axis. And then this second p orbital lies along the y-axis. And then the third p orbital lies along the z-axis. So these are our three-dimensional coordinates. Now in actuality, all three of these atomic orbitals are sitting on top of each other. So you'll notice that we would actually have what kind of looks like a six-leaf clover there, which isn't possible, but. So we have our x orbital, our y orbital, and our z orbital. And then the nucleus is somewhere in the middle there. Now remember that all three of these orbitals have the same energy. So we might not know for sure if an electron is in the xp orbital or the yp orbital or the zp orbital, but the probability is pretty similar. So as long as you know that an electron is in one of these two p orbitals, that's the important part. Now, d orbitals are a little more complex. You'll notice we have 5 different d orbitals. And again, this just specifies the orientation. So 4 out of the 5 d orbitals consist of 4 lobes. So they kind of look like 4-leaf clovers. And those are aligned either along different axes or between different axes. So you'll notice that, for instance, this first d orbital, xy, those are sitting kind of in between the x and y axes. And then down below we have this d orbital, which is aligned along the x and y axes. Now, I'm never going to make you draw these orbitals or memorize their shapes. It's just good to know where these different atomic orbitals are coming from. The last d orbital looks really strange. It kind of looks like a p orbital with a little donut around it. And again, all of these shapes come from computer modeling. So it's not something that you would be able to determine on a piece of paper, for instance. And then f orbitals are insane. So there are 7 f orbitals. And again, those are just indicating different directions that the orbitals are facing. So you'll notice that each of these f orbitals on the right-hand side, so 6 out of the 7, look like 6-leaf clovers. And then this one over here is kind of doing its own thing, so it kind of looks like a p orbital with 2 donuts around it. And again, I don't expect you to memorize these shapes or which orientation they're in. This is just to show you what those probabilities look like for where an electron can exist. Okay, so we'll end the lecture here. Just to summarize, we can locate where an electron is based on its shell, its subshell, and its atomic orbital. So next time we'll talk about how to actually determine where an electron is.